1.4 is continuity and one-sided limits. So we first have to talk about what is the definition of continuity. So a function is continuous at a particular x value, so at say a point C. If f of c is defined, that means that there is a dot there. There is a point or a y value that exists at c. The limit of f at c exists, which means if you're coming from the left and you're coming from the right, there is a point there. And it also means that that limit has to equal f of c. So if you're thinking in terms of a picture, and I tend to draw kind of the same picture every time. So we're going to look at this here, and we're going to say our c is here. So the first one is saying that there has to be a point at c. There has to be a y value right there. So the next one saying is the limit as you come from both directions. That limit has to exist. So if we come from the left and we come from the right, we have to go to that same y value, which again, if you see that, that is the case. So, and that y value that you come to has to be f of c. And you can see that that happens. Now, one thing that I think of as continuous is if you start to trace a point or trace a function, then you should never pick up your pencil. If it's continuous, you should never have to pick up a pencil. So there shouldn't be any holes. There shouldn't be asymptotes or gaps when you are looking at a graph. So a function is continuous on an open interval. Open interval means we're not looking at those endpoints. If it is continuous at every point in the interval, so again, you can't pick up that pencil. You should be able to draw it all the way through without picking it up. So it has no holes, it has no gaps, and it has no asymptotes within that interval. We have two different types of discontinuities. So discontinuities are places where it's not continuous. We have what's called a removable discontinuity and a non-removable discontinuity. So removable means, I think of it as you can take it out. So if we looked at a graph and say it's just a graph of a line, but maybe it's a line that has a little hole in it. So if it's a removable discontinuity, that means that if I put one dot there, then that would make it continuous. So by putting that dot there, I have made that a continuous function. So that's what we think of as a removable discontinuity. Non-removable would be, okay, we have this big gap maybe. So maybe my function is something like this, and I have a gap between them. So notice it's not continuous. I can't just draw it without picking up my pencil. I have a gap. I have to pick it up and move it. So that's a non-removable. I can't fill that point and make it a continuous function. So I could fill that hole, but it's still going to have that gap in between. So that would be an example of a non-removable. Another non-removable is when we do have asymptotes. So let's say we have something that looks like this. So we see that there's an asymptote here. That would be another one that there is no way to fill in a point to make that a continuous function. So this top one is removable, and these bottom two are non-removable. So just kind of gives you a visual of what we're looking at. So if you graph this first one, we're going to have a function that looks something like this. So you can see here, because it's giving you an asymptote here at 0, because it's undefined when x is 0, then that would tell you that this is a non-removable. So it is not continuous because it has that asymptote there. So the next one is your cosine of x. So if you think of cosine of x, you have to remember it starts at the top, goes down to the bottom, back up to the top. But remember, it's a cyclic function. It technically goes on forever. So we have something that looks like this. So if you were to draw this, it does go on forever. It doesn't stop. You don't have to pick up your pencil. So this would be something that is continuous. Okay. if you look at the next one, so think back to what we were doing earlier, we could factor and get something that looks like this. And then we'd have x plus 2 and x minus 2. Now, this is where removable kind of comes into play. So notice we can cancel. So if we were talking about a limit and finding a limit here, if we were to say the limit as x goes to 2, we can't do that direct substitution here because we get 0 in the denominator. But what we did before is we canceled. We removed that discontinuity to be able to find a limit. So when you can cancel them, it is a removable discontinuity. Now, what we would say here is this is not continuous. And we'd say it has a removable discontinuity at x equals 2. Now, we still have this, if we plugged in a negative 2, we'd still get something that's undefined. So we would say then it has a non-removable discontinuity at x equals negative 2. So in this case, it's not continuous, but it has two problems. It has a removable discontinuity at 2 and a non-removable discontinuity at x equals negative 2. So up here at the top, when we said non-removable, we should also say that it is a non-removable discontinuity here at x equals 0. So you will state it's not continuous or it is continuous. And you would have to state also, is it removable or non-removable, and where are those discontinuities located? So when we are talking about limits, when we've kind of done this already, we talked about limits coming from the left, limits coming from the right. So if you see a plus sign, that means you're coming from the right. If you see a little minus there by the C value, which is usually your number, you're coming from the left. So think of this as your negative x-axis. So you're coming from the negative x-axis. This is your positive x-axis. Now, we have to do this on both sides to make sure that a limit exists. But sometimes we just want to know what's happening on the left, what's happening on the right. So let's look at this greatest integer function here. So we want to find the limit of all of these. So let's go from the limit as x goes to 0 from the positive side. So remember, this is your positive x-axis, this is your negative, as we're getting close to 0. So as we're getting close to 0, what is our y value getting close to? Well, our y value is getting close to 0. But if we're going from the negative side, and we're getting close to an x value of 0, what is our y value getting close to? Well, that one's getting close to a negative 1. So if we look at this last one, we're looking at the limit as x goes to 0 of that greatest integer function. Well, notice that these two values don't match. In order for that limit to exist, those two values have to match. So we would say this limit does not exist. We have a gap between there. It's not continuous. These two things are not the same. So let's look at another one, and we're going to look at this piecewise function. So we kind of need to look at the graph, and this is a little bit more difficult, and I don't have the graph here for us to look at, so we're going to have to kind of put it together. So if you're looking at this piecewise function, it divides at 0, so this is, do we remember some of our algebra skills? So we're looking at that dotted line necessarily isn't there, it's just where the two things divide. So if we say we plug in 0 for the top function, we'd have 0 squared plus 3, which is really 3. Now, because there is nothing there, it's really an open circle. So we're going to use this for blue. And then if we plug in, let's say 1, then we would have 4. And we know this is a quadratic, so we're going to say it looks something like that. The other one is a line. So if I plug in 0, I get 3. 1, 2, 3. So notice what happens is I'm going to fill in that dot, that circle. And then we would have, if we plugged in, say we want x values that are, oops, I think I have this on the wrong side. Let's switch this around. So this is x is greater than 0, so our quadratic should be on this side. our line should be on the other side. So if I plug in 1, we would have 2, so on and so forth, and our line would go this way. So what is the limit as x goes to 0 from the positive side? So again, we are traveling from the positive x-axis, so we would be going to 3. If we're going from the negative x-axis, we are also getting close to 3. So because these two values are the same, then our answer, that limit does exist. So we get 3. And that is filled in, so that would be a continuous function. So I apologize for my graphs being backwards. Pay attention to those signs. And then we have our quadratic on the left, our line. Again, we have those two values coming from each direction being the same. Therefore, that limit exists and your function is continuous. So that goes to the existence of a limit. So just like we said, the limit exists if you're coming from the left and the right and they're getting the same y values. So if those y values are the same, then that limit does exist. And that's all this is saying. It's just a bunch of words, but really if you get the same y value from the left, same as you do from the right, that limit exists. Those properties of continuity, so scalar multiplication, adding and subtracting product and quotient, those apply here just like they did for limits. So we have the intermediate value theorem. So if f is continuous on a closed interval, notice it's a closed interval, so we are including the endpoints this time. And it says k is the number between f of a and f of b. Remember, f of b and f of a would just be y values. Then there's at least one number c in the interval from a to b that f of c equals k. So really this is a lot of letters, so we need to see what does the picture look like. So what it is saying is if we have an interval from a to b, so I'm going to say this is a and this is b. And we have, I'm going to say f of a is right here. And we're going to say f of b is up here. That means those are just the y values associated, and we have some function in between. So that's what this first part's saying. We have two endpoints, and we have our y values. So it says there's, in that interval from a to b, and there's a number k between f of a and f of b. Then there's at least one number c in between a and b. So there's some number c in between here that f of c is equal to k. So f of c would have to be somewhere in between there. So we have this point, and that would have to be in between those y values because there's some k, and they're using k here in between. What is this used for? Why is this important? This is actually used to help verify that zeros exist. So what would that mean? So let's think about it in terms of that. What if our f of a is down here and our f of b is up here? So here is our a and here's our b. So here's my function. Well, if I know that f of a is negative and f of b is positive, then some point here it has to cross the x-axis. So it has to have a 0. This would work the other direction as well. If you had your f of a above the x-axis and f of b below, as long as one is positive and one is negative, then we know some point in between there, it has to cross that x-axis. So it has to have a 0. So if we're looking at this, it says by the intermediate value theorem, does this function have a 0 on this interval? So really what we have to do is we have to evaluate. Well, actually, we need to check some other things first. So notice it has to be continuous on that interval. So if we look at this, this is a polynomial function. So since it's a polynomial function, we know it has to be continuous. So we have to check continuity. Once we know it's continuous, then really what we have to find, we have to look at our endpoints here. We need to find f of 0 and f of 1. So if we plug in 0, we get -2. If we plug in 1, we get 1 plus 3 minus 2, which is going to give us a positive 2. That means that at 0, we have -2, so we would be down here. And at 1, we're going to say 1's over here, we're going up 2. So we know 1's on the bottom and 1's on the top. That would mean if it's continuous, the only way for it, or it has to have a 0 because it's continuous. You can't pick up that pencil. Do we know exactly where it is and what it looks like? No, but by the intermediate value theorem, we can say it does have a 0. It has to cross in order for me to get there. So we would say, yes, it has a 0 by the intermediate value theorem. So it is used then to try to test to see if there's a 0 on a particular interval. So what are we looking for again? We are looking for one of those values is positive and one of them is negative. Do we know it only has 1? No, we don't necessarily know that. We just know it has at least 1 0. It has to cross at some point for me to get from point A to point B, or from the beginning of the interval to the end of the interval. It has to cross that x-axis.